This is the Temperature Control Lab team. Our group consisted of Tom Krotzer, Derek Draper, Mitchell Stallings, and me, Dallin Whitaker. We're going to first have Tom talk a little bit about the hardware that we used for our apparatus.
Okay, here we have our Arduino, and on top of the Arduino we have a breadboard. And on this breadboard you can see there is a heater, which is just a transistor, and a temperature sensor, which is connected to the heater with some thermal epoxy. And so that's our heating system. And then right behind it we have the fan, which blows air across the heater and the temperature sensor and cools them down. So there are basically two circuits on this breadboard that are smushed together. One circuit powers the heater, and the second circuit uses this little transistor and pulse width modulation and the battery to power the fan. So the Arduino modulates both the fan and the heater from these two digital pins right here, and we've created a PID controller to control the temperature of the temperature sensor at a certain set point however we like.
Okay, so to go into a little bit of the theory, what's going on behind the scenes here, this is just an energy balance that is derived with the assumptions of black box radiation and negligible conduction through the transistor. Essentially, this describes how the temperature changes with our system, with the heat input being Q and our fan speed controlling this H value right here. So because that model is rather complicated, we decided to use just a first order plus dead time model outlined right here. This model will allow us to put a controller on our system and allow us to get the temperature control that we want. Tom already talked about our apparatus and essentially using the fan and the heater in sync, we were able to control the temperature. The first thing that we did with the Python code that we had from our original control lab, we stuck in some constraints here. Let's see if I can find them. Yep, right here in the for loop. So basically, we extended the outputs first off from 100 to negative 100. And basically, if the output was negative, right here, if the output is negative, then it's going to write to the fan a positive number, basically the magnitude of the output that we want. And then if it's positive, it's going to write to the heater. So essentially, we had one PID controller that was controlling our system. That gave us results outlined here in this graph. As you can see, there's kind of a lot of random oscillation that happens right around the set point. And from what we were able to tell by trying to tune the parameters, we weren't unable to get rid of this oscillation. So because of that, we decided to make our system a little bit more complex by adding another PID controller, and this is outlined in this file right here. So here's the PID for the heater and a PID for the fan. Both of those were running in sync with each other, but still, after implementing this change, we still had a little bit of oscillation on the heating, because we saw here, especially in the bottom when you look at the two outputs, the heater and the fan were kind of fighting each other for control of the system. To negate that unfavorable behavior, we included a few stipulations inside of the PIDs. These stipulations included basically limits inside of the PIDs. For the heater, if the system was cooling, the heater would stay off until it was reasonably close to the set point. That's what this if statement does right here. For the fan, if the system was reasonably close to the set point, we wanted the heater to have non-competitive control of the system. And that's accomplished here with this set point. These if statements right here, these set point changes. Anyways, so going back to the results of that, when we tested that system, we were able to find right here in figure 5 that we accomplished nominal control of our system. As you can see, this graph right here demonstrates what our system looked like without the fan. and this demonstrates what it looked like with the fan and nominal control parameters. Essentially, we were able to decrease this cooling time constant by over 100 seconds, or 80%, and we were able to decrease the overall error by almost 40%, or 37%. In conclusion, we were able to substantially enhance our temperature control upon adding a cooling component, or the fan, and we found that the two separate PID controllers yielded nominal system control. If we were able to spend more time on this project, we would be able to perhaps parameterize the energy balance that was derived in the theory section and use that to obtain optimal parameters. So we had a lot of fun with this project, especially applying what we learned in class to a real-life situation. Thanks, Dr. Hedengren, for all your help, and especially for the Arduino and the PyFormata code you provided. Stay classy, Provo, and have a great day.